A couple of days ago, I unloaded a simple square root finding algorithm named bisection method. In that video, I didn't even explain a thing because what that method works is too straightforward and easy. Bisection method just seeks for the root by repeatedly bisecting the interval defined by the two values with the opposite signs, and then selecting the subinterval in which the function changes sign and therefore must contain a root. It just tried to narrow down the interval and give us the good enough candidate after some iterations. It is a simple and robust, but its convergence rate is somewhat slow, so I am going to suggest a slightly different way. The name of this method is NewtonRaphson. Would you start with an equation where x squared minus k is 0 instead of the equation where x squared is k? Since the original function is quadratic, it is difficult to solve the square root right away. Therefore, in the Taylor series that mimics the quadratic function, a linear function including only the first order term, that is, a method that mimics the original function with a straight line is used. The slope of this line is naturally different for every x. So by calculating the slope, you can find the equation for this line. And when the y value of the equation of the line is 0, the square root can be obtained using the x value. To summarize, you can gradually approximate the square root using the following formula. If you put the current square root value xn, you can see that the slope of the function and the next square root value xn plus 1 are derived using the function value. The problem is that you have to use differentiations to find the slope of the function. Fortunately, the derivative of a quadratic function is very easy. For those who are not familiar with differentiation yet, I have attached the square root of the quadratic function in the box on the right. Finally, repeat until the absolute value of the difference between k and the square root squared obtained by the NewtonRaphson method lower than the desired threshold. Here is an example of finding the square root of 20. As you can see, y is equal to 0 has two square roots. The problem is we don't know what these numbers are. First, let's put 5 as initial value for predicting the square root x0 in NewtonRaphson method. As a result, it can be seen that the y0 value of the function is 80. Then, the equation of the tangent line approximating x0, y0 of the quadratic function is obtained. For reference, you can just use the simple formula x1 is equal to x0 minus fx0 divided by f prime x0 we saw earlier. I'm looking for the tangent equation because I have to explain this method visually to you here. So, anyway, this finally yields y is equal to 20x minus 120. Now, let's find the point x where this line meets y is equal to 0. That is the next square root, that is update x1. As you can see, the value of x1 is 6. When x1 is inserted in the quadratic function, you can find the yn value. So its value is 16. Now let's set up the equation for the straight line tangent to the quadratic function by putting the value of x1 and y1. The result was y is equal to 12x minus 56. So when this line holds y is equal to 0, what value does x have? Wait a minute, I think you already got the value similar to the square root of 20, don't we? So, shall we zoom in on this graph? The square root estimate of x2 resulting from applying the Newton-Raphson method twice is now 4.67. When you zoom in, the estimated actual value is still a little bit different. Shall we proceed one more time? Putting x2 into quadratic function, and it yields 1.81. So let's calculate the equation for the straight line with the slope tangent to the x2, y2 coordinate. And the equation of this line is y is equal to 9.34x minus 41.81. That comes out. When this line is y is equal to 0, you can see that x becomes 4.48. That is, x3 is 4.48. Then, shall we take a closer look to see if the desired result has been achieved? To express the square root of 20 as a decimal point is about 4.472, and the square root estimate we got from the Newton-Raphson method is 4.48. How much difference will it be? Well, wow, looks pretty good in my opinion. I overcame the error to almost 4 decimal place in just 3 iterations. Now, the explanation seems to be enough. It's all left to implement the Newton-Raphson method in Python. I don't think I need much explanation about the code. This is because I have informed you of all the necessary part. If I talk too much, it gets boring. Just run the code and fill it. That's it. And run the program. Okay, as you can see, the square root was found perfectly. It cannot be easier than that. The source code can be downloaded from my GitHub, so please refer to it. I hope this video will help you understand the NewtonRaphson method. If you like this video, please subscribe and like it. Thank you.